general relativity step by step. Last time I was looking at the 4 velocity, and I made the observation that if you take the dot product of the 4 velocity with itself, you always get -1, which is an astounding and very useful fact. I'm going to try and generalize the notion of dot product to A dot B equals something, some scalar, where A and B are 4 vectors. And I'm going to wonder what A bar dot B B bar is, equals what? Well, we hope that A bar dot B bar equals A dot B. We hope, we want this. We want this to be true because we want the scalar dot product to be frame independent. So the way to think about this is that if I give you a regular 3 vector, if I say vector u equals just, how can I express this one? u1, u2, u3, and v equals v1, v2, v3, just normal 3 vectors, just like you had at school. So u dot v equals sigma ui vi, which is just the dot product. So u and v look like this. There's u and there's v. With respect to some coordinate system, which I'm going to draw in a different colour. What colour shall I choose? I'll choose green. X and y. And then somebody comes along and says, I don't want you to use those coordinates. I want you to use some tilted coordinate system here, x and y, in which the coordinates of u, the vector, and v, the vector, are going to be different. Let's go back to black. So now we've got u dash, and that's going to be u dash 1, u dash 2, u dash 3. Got my dashes and the 3's the wrong way around. Dash 3. And of course v dash equals v1 dash, v2 dash, v3 dash. We hope that sigma ui dash vi dash, which equals u dot v, u dash dot v dash, we hope that u dot v equals u dash dot v dash. Because the dot product of 2 vectors has got a meaning which is independent, or it should have, well it does have, and it's a desirable property. It's got the property that the dot product is independent of the particular coordinate system you express it in. And we've seen this in tensor calculus, and we're going to look at it in special relativity now. But this is quite an important one. If I have A and B are 4 vectors, we want A bar dot B bar to equal A dot B, where the bar expresses means that the coordinates are expressed in a different coordinate system. Well, let's just work out what that is. A dot B equals G alpha beta A alpha B beta. So writing it out in matrix form, we've got this -1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. Well, which way around am I doing it? There's my B, B0, B1, B2 and B3. Every time I do this it pains me because I want to put the time coordinate last and it comes first. A0, A1, A2, A3. And that of course equals minus A0, B0 plus A1, B1 plus A2, B2 plus A3, B3. Okay, so what is A bar dot B bar equals what? Well, A bar 0, bar 1, A bar 2, A bar 3 equals gamma, gamma beta 0, 0, gamma beta, gamma 0, 0, 0, 0, 1, 0, 0, 0, 0, 1 times A0, A1, A2, A3. So that's just the Galilean, not Galilean, the Lorentz transform. And similarly for B. So now we can take a dot product of these two things. A bar dot B bar equals, let's see if I can get this right, B0, B1, B2, B3. And I'm not making this explicit, but I'm actually taking the transpose of the matrix, but it's symmetric anyway, so I don't need to worry about that. Gamma beta 0 0, gamma beta gamma 0 0, 0 0 1 0, 0 0 0 1. This thing here being B bar. Actually, it's the transpose of B bar, but I keep on banging on about that. I think I've said that enough now. 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. This thing here is the fundamental tensor. Expressed in any units you like, it's always the same. Whatever, any coordinate system you like, it's always the same. Now we need to Galilean transform, Lorentz transform A. Gamma beta 0 0. While I'm writing this, just want to make the observation that the Galilean transform is far from obvious. It's far from trivial as well. I've spent a long time dealing with fluid mechanics, in which the Galilean transform is the important thing. And the Galilean transform is little short of a miracle, as far as I can see. Oh no, that's A, isn't it? I should stop trying to multitask. I'm trying to talk and write. Making mistakes. I'll shut up and just write. This thing here is A bar. Okay, so that's a bit of a mouth. Well, it isn't. It is what it is. It's complicated, but we just got to plug our way through it. So I'm going to evaluate this product. I'll do it in a different colour. I'll do it in red. I'm going to grab those two things there and evaluate them, and then multiply by that Lorentz transform. There. Okay, so what have we got here? Let me just... Oops, it keeps on doing that tonight. It drives me nuts. Okay, so let's just work out what that is there. That's going to be minus gamma, top left. I'm going to go do the top row first. That's going to be gamma beta 0 0. Second row is going to be minus gamma beta gamma 0 0. And these are going to be just the same as last time, aren't they? They're just the same as last time. Wrong. And then we need to put this one here. We need to multiply by the old Lorentz transform again. Pinching a little bit. Equals. Oh, top left. We've got a minus gamma squared plus gamma squared beta squared. Doing the top row first. Here we've got a minus gamma times gamma beta plus gamma beta times gamma 0 0. Second row. We've got a minus gamma beta gamma second row. We've got that term times this term. We've got a gamma times gamma beta. Is that a plus or a minus? That's a plus. Plus second. I'm doing second row, first column. So we've got gamma squared beta there. Whew. Second row, second column, what have I got there? I've got a minus gamma squared beta for that term times that term plus gamma squared. Wonderful, 0 0. Those are easy. That one's easy. That one's easy. That one's easy. Well, I dare say we can calculate this. Let's look at the top left element. Top left equals minus gamma squared plus gamma squared beta squared equals minus gamma squared 1 minus beta squared equals minus 1 over root 1 minus beta squared 1 minus beta squared equals minus 1. That's nice. Oops, that drives me nuts when that happens. And of course this term cancels out as well. So what we're left here is that the whole matrix equals minus 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Ha! Right. Which equals G, the fundamental tensor. Actually, sometimes people write it as eta, alpha, beta for the flat Minkowski metric. Okay, so I've multiplied all these three matrices together, and that was just equal to the regular metric tensor. So that equals minus b, I'll pinch in a bit. No, it doesn't. It equals b0, b1, b2, b3 times the product of all those matrices there. I'm putting my b's first and my a's first. For some reason, I'm putting my b's first. I wonder why that is. Yeah, doesn't matter. Symmetrical anyway. 0, a1, a2, a3, which equals a dot b. So just to summarize this whole thing, a and b are 4 vectors. A dot b equals a bar dot b bar, where the bar means the 4 vector as expressed in a Lorentz transformed coordinate system. There it is. So the dot product is coordinate independent, or frame independent. Frame independent. Beautiful. Stop there. Took longer than I expected that.